All right, we're on to our last part of this lecture on stoichiometry. How much stuff do you make in a chemical reaction? Now, there's one other little issue I haven't brought up yet. So let's just kind of briefly review just for a second, right? So far what we've been doing is basically, I tell you how many grams of one thing you start with in a reaction. You tell me how many grams of something else you make in a reaction or you use up. So the grams of something else involved in the reaction. So the way you do that takes you 3 steps, doesn't it? Grams of A to moles of A, moles of A to moles of B. B is like some other compound, and then moles back to grams. Now all this steps involves, well, the first one, grams to moles, hey, you use your number on the periodic table. That's how many grams makes 1 mole. Then moles of one thing to moles of something else. Oh, to do that, that's where we use the coefficients, right? The coefficients of the reaction. So Rx is sometimes shorthand for a reaction. And then finally, moles back to grams. Oh, you look up the number. Maybe you have to add up the number on the periodic table. That's how many grams makes a mole. All right, so grams to moles, moles to moles, moles back to grams. So that is kind of how we have figured out how much stuff is in a reaction, involved in a reaction. Now, let me go back to some of the examples you've already seen me work out. And I want to bring up one other little issue that we haven't talked about yet. All right, let me flip to the next slide. All right, so one example we talked about eating a little antacid tablet, and we said, oh, if you eat 0.2 grams of this antacid tablet, I asked you, how much water did you make? How much water? How many grams of water would you make? Oh, we saw that earlier in this lecture, didn't we? And then we did another example where I talked about, well, what if you burn some alcohol? So like this is alcohol, and if you start off with 84.9 grams of alcohol, I asked you, how much carbon dioxide would you make? Now, there's one thing that I haven't brought up, which is in both of these cases, whether we're eating a Tums tablet or burning some alcohol, for this reaction to happen, you also need the other chemical, don't you? Like the tablet by itself isn't going to react. It has to be around acid. It has to be around your stomach acid. And not only that, it turns out one thing I haven't really mentioned is not only do you have to have stomach acid around HCl, you need to have enough of it so that the reaction can keep going until all of the tablet is used up. So that idea that we have plenty of the other chemical to do the reaction, sometimes in chemistry land, we call that being in excess. So I was kind of assuming that there was plenty of acid in your stomach and the reaction would quit when the tablet was gone. And the same thing's true for the alcohol example. So I was assuming that the reaction would quit, this burning alcohol, when all the alcohol was gone. Like there's plenty of oxygen from the environment or the room or whatever. So the oxygen is, in other words, in excess. So we could calculate the amount of carbon dioxide you would make just worrying about the alcohol. Now, there's going to be plenty of situations in the world where you don't know if that's true. You don't know, does the reaction stop because I ran out of this compound or because I ran out of this compound? So reactions are going to quit when one thing is all used up. So a problem like this, where you're not sure which one you're going to run out of first, that's called a limiting reactant problem. And that's kind of what we're going to talk about in this last video. All right. So let me tell you a few notes about it and then we'll do an example. Okay. So this is going to be a limiting reactant problem. All right. A limiting reactant problem. Now, in a limiting reactant problem, we're still going to try to figure out how much stuff we're going to make in a reaction. All right. So I see a reaction up here, aluminum, and I guess that's iron 3 oxide turns into aluminum oxide and iron. So the goal in this case is going to be to figure out how much iron are we going to make, how many grams of iron we're going to make. But what makes this problem slightly more challenging than the ones you've heard so far is that I tell you the amounts of both chemicals you start with. I tell you in the question, you're going to start off with 42 grams of aluminum And I tell you, you're going to start off with 55 grams of iron 3 oxide. And I ask you, based on those initial amounts, how much iron, how much Fe do you create? Now, how do I know this is a limiting reactant problem? Well, the way I know is because you are given two amounts to start with. So I tell you the amount of each reactant. So what that is trying to tell me is, hey, figure out the amount of iron that you're going to make, but also you're going to have to figure out which chemical do you run out of first. And when that chemical is all used up, that means that the reaction will stop, and that's going to determine how much iron we can create. So we're going to get to this example in a minute. Now, before we do that, let's do like a little analogy. All right, so what is this sort of similar to? All right, let me flip over and let's start off with a little analogy and then we'll get back to this problem, okay? All right, so in this analogy, basically like, what is a reaction? A reaction is basically like a chemistry recipe. It's like a cooking recipe. So before we get into chemistry, let's just talk about maybe a cooking recipe, okay? So let's say, you know, your grandma, she used to always make you these chocolate chip cookies that you love to eat. And her recipe said, mix 1 tablespoon of chocolate chips with 2 tablespoons of flour, and hey, you're going to make 1 cookie. Grandma's favorite recipe. Chips and flour, a tablespoon of chips, 2 tablespoons of flour, you get 1 cookie. All right, now obviously this isn't a super great recipe because there's no sugar or eggs or whatever, but hey, we love Grandma. This is the way Grandma used to make them, all right? So she would just mix chips and flour together and get you that cookie to eat. Oh, it tastes so good. All right, now, um, let's say you decided, hey, tonight I'm missing my grandma. I'm gonna make some cookies. And you hunt around in your cabinet and you find in your kitchen cabinets 7 tablespoons of chips. So you actually own 7 tablespoons of chips and you own 10 tablespoons of flour. And again, this is our recipe. And I say, well, based on what you actually own, how many cookies could you make? All right. How many cookies can you make? So I'm going to just let you think about it for a second. Your cabinet has 7 tablespoons of chips, 10 tablespoons of flour. How many cookies could you make using Grandma's recipe? All right. It should be 5. Let's see. If you didn't get 5, let's talk about why it's 5. So basically, what you would do is you would say, based on the amount of chips and the fact that I need 1 tablespoon of chips, I have enough chips for 5 cookies. And then based on the amount of flour, and the fact that I need 2 tablespoons of flour for a cookie, I have enough flour. Oh, I miswrote here. This should say 7, shouldn't it? I have enough chips for 7 cookies. I'm sorry, I messed that up. All right, now based on the flour, I have enough flour because I need 2 tablespoons of flour for a cookie. I have enough flour for only 5 cookies. So how many cookies are you really going to make? Well, you're only really going to be able to make 5 because when you are done making those 5 cookies, you'll be out of flour. In chemistry land, the thing you run out of, in this case like the flour, the thing that we're going to use all up, that's called the limiting reactant, or you might hear it called the limiting reagent, limiting reactant. Now, turns out, after you get those 5 cookies, you're still going to have some chips left over. You would still have, because you would have used, what, 5 tablespoons of chips? You're still going to have extra chips left over, I guess 2 tablespoons. So there's more chips than you will have more chips than you really need. So you're going to have extra chips left over. So the thing that you have extra of in chemistry land, that's called being in excess. So we're going to do kind of the same thing in our chemical reaction. If you know the amount of both ingredients, what we're going to do to see how much stuff we can make is we're going to calculate how much can we make based on each ingredient. Based on the chips, I can make 7 cookies. Based on the flour, I can make 5 cookies. And once we can see how much we can make based on the both amounts, the real amount is going to be the lower value. So the answer that gives you the lower value, or the lower answer you get, that's the real amount you're going to make. Because once you make those 5 cookies, you're done. You can't make any more. It's going to be the same thing in chemistry. When you're done, when you use up the limiting reactant, the reaction is going to quit and you can't make any more stuff. All right, so that's kind of like the idea. Now, the calculations, there's some good news and some bad news. The calculations to figure out how much stuff you can make, it's the same ones we've been doing. Grams to moles, moles to moles, moles back to grams. So that's going to be how we can figure out how much stuff we can make. The only reason this is tougher is you're actually going to have to do it for both reactants. You're going to take both amounts and see how much stuff you can make, and then the real amount will be the lower value. All right, so let's do an example, and hopefully that'll help it make a little more sense. So let's get back to that example. Now, that example that I showed you, it's a reaction, aluminum and iron oxide, and I actually did it. And let's go ahead, and I'm going to show you the video of what that reaction looks like, the one that I talked about a minute ago. What was it? Fe and, what was it? It was aluminum plus Fe2O3 turns into, what was it? Aluminum oxide and iron. All right, so I'm going to show you this reaction, and then we're going to calculate how much stuff we can make based on this reaction. I think I asked you how much iron can we make. We're going to figure that out. Okay, all right, let's look at this reaction first, and then we'll do some stoichiometry practice with it. All right, so we're outside, and I'm going to show you a little demo here. That's called the thermite reaction. So the thermite reaction involves mixing aluminum. So this is ground up aluminum. And I'm going to be mixing it with some iron 3 oxide, okay? So first thing we got to do is we got to mix them together. So we're going to put them together, and nothing's going to happen right away. So after I put them together, it's going to take a little time to react. So yeah, let me go ahead and do that. And I'm going to mix them in these flower pots right here. So in goes the aluminum oxide. So aluminum 3 oxide, also known as rust. And we're going to mix it with some aluminum. And let me stir it up a little bit. Now, after I stir it up, nothing's going to happen because I need to give this mixture a little energy to react. So I'm going to do another small reaction, which will create some energy. And then that'll start the main reaction. Now, one of the products of this reaction, as you can see on the screen, is iron. But it's not just going to make normal iron. It's going to make liquid iron. It's going to make molten iron. So this reaction is going to get up to about 1500 degrees. All right, so let's see. All right, I got it pretty well mixed, I hope. I'm going to put it in here. And now when that molten iron forms, you're going to see it's going to come out of the bottom of this flower pot. It's going to land in my bucket of dirt. All right, so I got to do another little reaction. This is a compound called potassium permanganate. And then I'm going to add a little glycerol. Now, nothing's going to happen for a few minutes here. That'll give me time to back up, and then we should see something. All right, so let me go ahead and do it. Let me go ahead and add a little glycerol. We'll wait a second. So it might take 30 seconds or more for it to start. All right, give it a second. Let me pick this stuff up. And we'll see if we get anything happening. We should here soon. All right. Oh, I'm looking. Boil, boil, toil and trouble. All right. Let's see.
Double, toil and trouble.
Oh, that's my English teacher wife trying to correct me. All right. Come on. Come on. All right. We got to give it a sec here.
Can we come look?
No. I'm hoping I get all react here. All right.
Elijah, stop right there. Don't get, well, you can move just a
All
little.
right. We'll wait. Come on. Come on. There it goes. So we're starting to get the glycerol reacting with the potassium permanganate. That'll start the main reaction. We'll be making some liquid iron. Watch for it to come out of the bottom here in just a second. And there you go. All right. now, oh, there's the liquid iron spewing out the bottom. So that got up to about 1500 degrees. So we're going to calculate how much iron did we make. All right, so I have a little crowd here. You can come up and look at it now if you want. All right, and I didn't even kill my own children, so I'll call that a good day. All right. Okay, so now you've seen that reaction. Let's see how much we made, right? So I showed you, you get this liquid iron, this molten iron, it forms, and this reaction gives off a lot of heat and light and all that. And I want to figure out how much iron did we make? How many grams of iron did we make? So good news, it's the same calculation we've been doing all class, all lecture. Bad news, you got to do it twice. We're going to take the 42 grams of iron that I told you I used in that demonstration when I went outside. I used 42 grams of iron. And we're going to start off with aluminum. 42 grams of aluminum, I should say. And we're going to take that 42 grams of aluminum and we're going to convert it to moles of aluminum. Then we're going to go from moles of aluminum to moles of iron, and then back to grams to see how many grams we can make based on the weight of the aluminum. All right. Now we're going to do the same thing again, but starting off with the 55 grams of iron oxide. So we'll start off with the 55 grams of this. Same exact steps. Grams of iron oxide to moles of it. Once you know moles of iron oxide, you're going to go to moles of iron. And then once you go to moles of iron, you'll go back to grams. So you're going to get the weight based on the aluminum, and you're going to get the weight of iron you can make based on the iron 3 oxide. You're going to get two answers. Which one's going to be the right answer? It's going to be the lower answer, just like with Grandma's famous cookies, right? Though a lower amount is the real amount, because that's when the reaction stops, when you make that amount. All right, so let's go ahead and do it. So just to remind you of the steps: grams to moles, periodic table, moles to moles, coefficients, moles back to grams, periodic table. All right. I'm going to go through it and I'll show you the work. I might go a little faster just because it's similar to what you saw, but if you need it to go a little slower, you can always rewind it, okay? All right, so let's do it. And I should tell you, I'm going to do it as one giant problem. You saw me break it up into several steps, totally fine, or you can do it as one giant question. Let's do the aluminum one. 42 grams of aluminum. We are solving for grams of iron. Grams to moles, moles to moles, moles back to grams. So grams to moles, that's the periodic table. Look up the value for aluminum, 26.98. 26.98, what? Grams equals a mole. Think about it for a second, think about it for a second. If we're trying to go from grams to moles, what are you going to do with the 26? Grams to moles, you got to put grams on the bottom, makes 26 go on the bottom, 1 mole of aluminum goes on top. Oh, we're done with the first step. Goodbye, grams. All right, now we got to moles of aluminum. Now we're going to go from moles of aluminum to moles of iron. Coefficient time. Put what you're trying to get rid of on the bottom. I'm trying to get rid of aluminum. Put its coefficient on the bottom, which is a 2. Put what you're trying to solve for on top. So I am asking you to solve for the amount of iron. So you would put iron on top and iron's coefficient on top, which is a 2. It should look like that. All right, what have I gotten rid of now? Moles of aluminum cancels. All right, now we're at moles of iron. Fantastic. One more step, we'll be done. Now that we have moles of iron, we're going to go to grams of iron. All right, so let me tell you, oh, it's right here. 50, what did I say? 55.85. 55.85, what? Grams equals a mole. All right. You have moles currently. You have moles of iron. How are you going to get rid of moles? What are you going to do with the 55? You need to multiply. So if moles of iron are there, you put moles of iron on the bottom, and then you put the weight off the periodic table on top. And now if you work this out, you should get 87 grams. 87 grams. All right. So hopefully this looks right to you because, all my units are canceling. That's one way I know that it's right. The only other thing, because someone asked me about this already, which is in this first and last step, it's always for 1 mole. All right, so the only time you're going to use the coefficients is in the middle step, the 2's, okay? So hopefully that looks right, okay. All right, now let's go ahead and we're going to do the same exact work, but we're going to start off with the weight of the iron 3 oxide. All right, so let me erase it, just a couple of things we don't need anymore. And we're going to do the exact same calculation, but starting off with the other ingredient. 55, my right color. Oh yeah, that's fine. We'll do blue again. 55 grams of iron oxide. Grams to moles. Moles to moles. Moles back to grams. Let's get an answer. Okay, so grams to moles, periodic table. Grams to moles, that's your periodic table. You have to add up the weight off the periodic table for that compound. The compound, again, we're starting off with iron oxide. So you need to add up off the periodic table these guys. 2 irons and 3 oxygens. All right, you know what? I'm going to let you figure it out. Go ahead and add it up. I don't even have it in front of me, do I? I don't even have it, do I? I don't know. I think I do. What do you get when you add it up? Add up 2 irons and 3 oxygens. When you add it together, I hope you got 159.70. That's what I came up with. Okay. 159.70. What? 159.70 grams equals a mole. Always write that. Now you'll know what to do with it. You got grams. To get grams to cancel, you got to put grams on the bottom. And that makes the 159 go on the bottom. And 1 mole goes on top. It should look like that. All right. All right, now let's move on to the next step. For the next step, let's go ahead and work it out. So to work it out, oh, by the way, this would be moles of iron. All right, and so now we're ready to go from moles of one thing to moles of the other thing. Coefficient time. Oh, I'm sorry, I miswrote here. This should be iron oxide, shouldn't it? Okay. All right, so we're going to go from iron oxide to iron. We're going to cancel out iron, and then we're going to solve for Fe. So if you don't see anything, again, the coefficient right here is a 1. And in front of what we're solving for, it's a 2. So think about what you're going to do with those coefficients for a minute. Well, you end up having, will you end up multiplying by 2 or dividing by 2? Which one are you going to do? Multiply by 2. If you have iron oxide here, it's got to go in the bottom of the next step. Goodbye, iron oxide. I'm trying to get rid of you. That makes its coefficient go on the bottom. The coefficient of what you're solving for goes on top. All right. At this point, let's see where we're at. Grams, gone. Iron oxide, gone. Now we have moles of iron. So I just need to convert from moles of iron to grams of iron. So the way I would do that is I would use the weight off the periodic table for iron. So iron again is 55.85 grams equals a mole. All right, if we work that out, it's going to look kind of the same as the one above, honestly, isn't it? Because we have iron here, moles of iron. We need moles of iron to cancel. Where does that mean you put moles of iron? If it's right here, make it go away, put it on the bottom of the next step. Oh gosh, let's try to be a little better. Same color. So we'll put moles of iron on the bottom. And then the 55 grams goes on top. It should look like that, 55.85. Okay, if you work it out, if you type this in on your calculator, you should get 38 grams. So when I did that reaction outside, how much iron should I have made? The iron, it ended up kind of going out the bottom of the clay pot. How much iron should I have made? I should have made 38 grams. I should have made 38 grams. Okay? All right. So with that, let me just tell you a couple of terms here. the amount you should have made, there's a name for that in chemistry land. We should have made 38 grams of iron. That is called the theoretical yield. The theoretical yield. It's the amount you should make based on the reaction. The number that gives you the theoretical yield, the number that gives you the lower answer, this is the thing that I used up in that reaction. This is called a limiting reactant. So this would be the limiting reactant. The thing that I have extra of, I had enough aluminum to make like over 80 grams of iron. The thing I had extra of, this is called being in excess. In excess. All right. So theoretical yield is the amount you should really get. It's the lower of the two. And then the answer that gives you that lower, the number that gives you that lower answer is called the limiting reactant. And then the one that gives you the high answer, you have plenty of, that's called being in excess. All right. With that, I'm going to show you one last thing about this, okay? All right, let me flip over to one more slide here. All right, so one last thing I want to tell you. So based on the calculations that we just did, we should have made, what did we say again a minute ago? I think we said 38 grams of iron, all right? And that 38 grams, the amount we should have made, that's called the theoretical, that's an E there, theoretical yield. All right, now there's one last thing that you're going to run across, which is, you know, when I really did that reaction, I was thinking, based on the calculations, I should end up with 38 grams. Now, this is actually the iron. I don't know if I can show it to you. This is the iron. So it, you know, it melts and then it cooled down. I did that experiment yesterday, actually. So it's, you know, way cold by now. And actually, I tell you one thing that looks kind of funny. It looks like a turtle. How about that? Yay, maybe I'll sell this. It's a iron turtle. All right, swim away, a little turtle. All right, so when I get that iron, if I was to stick it on the scale, it may not actually weigh 38 grams. You know, things don't necessarily work out perfect, right? Maybe I didn't mix things quite right. Maybe some of the stuff didn't react the way I thought it would be. You know, there's things that can happen where the amount you really get doesn't quite match up with the amount you think you're going to get. So the way that we kind of compare how much did we really get to how much did we think we're going to get, that's something called a percent yield, all right? So a percent yield is basically just a way to compare how much did I actually get. So it's the actual yield divided by the amount you think you should have gotten. Theoretical yield. Theoretical yield. And you times it by 100 to make it a percent. So the actual yield, how would I get that? Well, I would just take this hunk of iron that got created in that reaction I showed you, and I'd put it on a scale. So I would just take what I made and I'd throw it on a scale. What does it weigh? The theoretical yield, that's what we got from the calculations, right? The grams to moles, moles to moles, moles back to grams, lowest answer, all that stuff. So that's from the math. And then you divide the two. So let's just pretend, and this isn't quite right, but let's just say if I actually made 14 grams of iron, what is the percent yield? So we compare what did we really get to what we think we should have gotten. All right, so the way you would do that is you would take the 14 grams and you divide by how much I think I'm supposed to make, 38 grams, and you times it by 100. If you work it out, oh, let me check my notes there. I got 37%. All right, so that would tell me I only got about a third of what I was expecting, 37%. All right, for example. All right, so hopefully that makes sense. Again, we'll practice this during Zoom time because this can be a little confusing as far as what all these terms mean and how to do the calculations, right? So if you have any questions, you can email me too, and I'll try to help you out. Otherwise, we'll practice this during our Zoom times, and I'll see you then. Bye-bye for now.